Hello everyone. My name is Jordan. I'm a postdoc working at IFI in Barcelona. And today I will be talking about two different projects I've been working on recently, which are related to the search for ultra-dark matter. So the first project is related to a search through a space-based gravitational wave detector, namely LISA. And the second one is related to a search with a classical test of the universality of freefall, namely MICROSCOPE. And so these works have been done in collaboration with Aurélien and Peter Wolf from Paris Observatory. Now, one of the things we don't know about dark matter is the mass of the dark matter candidate, the dark matter particle. So there are many candidates. The candidates I will be interested in are low mass candidates, which are usually called ultralight dark matter, where basically the mass spans from 10 to the minus 20 electron volt to roughly 1 electron volt. And so for these low mass candidates, you can show that the occupation number of the field is very, very large. And so in this case, the field is necessarily bosonic, and in fact is well approximated by a non-relativistic classical wave, which has this form. So here phi naught is the amplitude, which is related to the local dark matter energy density. And you have a wave that oscillates at the Compton frequency of the field and which moves at a relatively low speed, so 10 to the minus 3 times the speed of light, which essentially corresponds to the galactic velocity. So of course, this expression is valid in the solar system reference frame. Now, a second feature that is important is that in the galactic frame, the dark matter particles are visualized, which means that they do not have the same velocity, but actually they follow a specific velocity distribution, which is in the simplest models, a Maxwellian Boltzmann distribution, which looks like this. And so it means that actually the field is not completely monochromatic, but it's a stochastic superposition of classical waves where basically each contribution has its velocity that is randomly chosen in this velocity distribution. And so it means that the field has a specific Lorentz time, which is roughly 10 to the 6 times the period, and a specific Lorentz length. And so as I will discuss later, this feature will be important for the second part of the talk. Now, let's look a bit more into the dark matter candidates specifically. So here I would be interested in a pure scalar field, so the dilaton field phi, which is linearly coupled to the standard model this way. So in different colors, you have different standard model sectors, and then the various D's are coupling constant. Now you can show that this interaction Lagrangian leads to variations of several fundamental constants of nature. So the Fine-Structure constant alpha, the electron mass, and several linear combination of the light quark masses. Now, these parameters depend on the scalar field. And since the scalar field, of course, evolves with space and time, these parameters are not constant anymore, but they evolve with the field. Now, the thing is that the rest mass of test bodies depends on those parameters. And so it will oscillate in the same way. And here I added specifically a parameter Q, which basically tells you how the rest mass depends on the scalar field phi. And this parameter, of course, depends on the several coupling constants, but it depends on the mass number and the charge number of the element under consideration, which means that, I will show you a bit later, it leads to a violation of the equivalence principle. And so it can be searched in classical and quantum tests of the universality of free fall. And in fact, as I will show you a bit more in detail in the second part, a similar phenomenology arises with axions that are coupled to gluons. So basically, you have your rest mass, whose motion is governed by the Lagrange equation. And so as long as you have a mass which either depends on space or time, your test mass will acquire an acceleration, which in our case looks like this. And so you see that it's proportional to this Q parameter. And so if you now consider the differential acceleration between two test masses of different composition, then this difference here between the Q will be non-zero, and so you end up with a non-zero differential acceleration. Now, if you assume two test masses of the same composition that are spaced apart by a distance that is smaller than basically the coherence length of your field, they will just oscillate in phase. So nothing special for now. But if they exchange light signals, this current oscillation will induce a Doppler shift of light. And so this means that basically you can detect such oscillations in optical ephemerometers. And so, for example, the ones that are used for gravitational wave detection. And so this is what some people try to do to look at this kind of signal in, for example, the data of LIGO and Virgo. And we expect similar oscillation in LISA. Now, of course, here I'm assuming a monochromatic signal. So in Fourier, you will just have a monochromatic peak at the Compton frequency of the wave. Now for LISA, we know that LISA, at least we expect LISA to detect many monochromatic signals from very early binary spirals. And so in this case, the signal will be very similar in Fourier space because we'll just have a peak at the frequency of the wave. And so a natural question that arises is if in real data analysis, LISA will be able to discriminate the two signals since in Fourier they look like the same. And so this is the question we try to answer. And of course, this is an important question to answer because even though it might be obvious due to the differences, for example, in polarization between the dark matter and gravitational wave, if it happens to not be the case, so that LISA is not able to break the degeneracy between these two signals, then even if dark matter exists with frequency in the LISA band, this signal might be misinterpreted as a gravitational wave, and so in this case, we are not really able to detect dark matter properly. And so to do it, what we do to see if LISA is able to discriminate the two signals. So the first step is to generate in time domain a dark matter signal, DDM, with of course a specific realization of the dark matter parameters, using TDI second generation, and also of course using realistic orbits of the spacecraft. So in our case, Earth training orbits, and a substantial amount of time. So in our case, 1 year, so one full orbit. So for this signal, the SNR is around 50, so the signal is well above the noise. Now, the second step is to build a fast likelihood modeling in Fourier space, of course, because we deal with monochromatic signals, so in Fourier space it's much more convenient. And so, and then the idea is to use Bayesian inference to compare a gravitational wave model and a dark matter model that are both fitted to this dark matter data, and then to estimate how well these two models behave, and in particular, how well this gravitational wave model fits this dark matter data. So now I'm going to show you the results of the study. So the first thing you can do to try to estimate the efficiency of your model is to build the residuals and to check basically to look at the residuals power compared to the noise power. And so this is something that we do through a parameter that we can call the residuals to noise ratio. And so for the first model, so the dark matter model, we found that this RNR, residuals to noise ratio, is much more than 1, which tells us that the model correctly fits the data. So this is something that we can show. You can see here and on the right, where I show the paraspectral density as function of frequency of LISA noise in red, the dark matter signal in green, and then the residuals of the dark matter model in gray. And so you see that despite the fact that the signal is well above the noise, the residuals are well below the noise. And so this is what we want for a good model. Now for the second model, so the gravitational wave model, the RNR is much larger than 1, which means that the model does not really fit the data. And this is something that you can see on the right. So the green and the red curve are the same, but the gray curve now is essentially the residuals of the gravitational model. And so you see that the gray and the green curve have the same shape and same amplitude, which means that basically the model did not extract any information out of the data. And so, of course, this is not what we want. So from this, we already have an idea on the efficiency of the gravitational wave model. Now, a second thing you can do, of course, in the context of Bayesian inference, is computing the Bayes factor. And so in our case, we found a Bayes factor that is largely in favor of the dark matter model because it's roughly 1,000. And so from these two results, we can conclude that the gravitational model does not explain correctly the scalar dark matter data, and that this probably means that a priori LISA will be able to discriminate dark matter from gravitational waves. So of course this is a positive result, and even though it was maybe expected, it's still nice to check numerically if this really happens. So now let's look at the limit, the constraint that LISA could put to the various dark matter couplings. So on the left, it's the dilaton, several dilaton couplings as function of the mass of the dilaton, and on the right, it's the axion-gluon coupling as function of the axion mass. And in red, it's region of the parameter space that are already constrained by laboratory experiments. And in black, it's the expected sensitivity of LISA. And so you see that in some regions of the parameter space, LISA will be able to be the most sensitive laboratory experiment. And so, of course, then it's important to know if it will be able to recognize dark matter in a zero gravitational wave. And as I shown you before, it most likely will. Okay, so now let's go to the second part of the talk about axions. So here I will be interested in the axion-gluon coupling through this Lagrangian. Now you can show that this Lagrangian leads to a dependence on the pi mass to the axion. And so in the same way as before, since the rest mass of test bodies depend on the pi mass, then they will depend on the axion. Now the difference is that as you can see, the dependency is not linear in the field, but it's quadratic in the field. And so it means that you have other effects that arise from this oscillation and from this, not oscillation, but from this dependency. And one of them is that in presence of massive bodies, the axion field is perturbed. Basically, here in the equation of motion, you have a source term that depends on the matter density. And so essentially that tells you that you assume an incoming dark matter wave that is scattered off massive bodies. And so you have spherical waves that are emitted by this massive body, and which you need to take into account to be able to have the full solution. And so basically, you can show that the total axion field amplitude is modified. So you have the usual amplitude that is related to the local dark matter energy density, and then you have a function that contains the spherical waves, and that basically is dependent on the incoming wave velocity. And so in the axion case, these Q parameters that again tells you how the mass depends on the axion field is always negative due to the negative sign here. And so we have a scalarization effect, so the amplitude is actually amplified. Okay. Now in the same way as before, the rest mass that I shown you before leads to an acceleration of your test mass. Now, since here the test mass is quadratically dependent on the axion field, you don't have, I mean, you have time oscillating acceleration, but you have also static acceleration, which looks like this. And so again, it's proportional to these Q parameters that is, again, as in the dilaton case, atom dependent. So this acceleration violates the universality of free fall, and so it can be probed by classical test of the universality of free fall, like microscope. Now, a second thing I want to discuss is that, remember at the beginning, I told you that the dark matter field is actually stochastic. And in fact, it means that if you look at the field for a time that is larger than the current time, you really have a stochastic superposition. While if you look at it for a time smaller than the current time, you have effectively a monochromatic wave. But the monochromatic wave still has a stochastic contribution because you still need to randomly choose the velocity of the wave in the velocity distribution. And basically, you can show that this stochastic component can be equivalently described by an amplitude, stochastic amplitude alpha, that basically that follows a Rayleigh distribution. And so now, basically, the acceleration is not only proportional to this term, but it's also proportional to alpha squared because it's quadratic in the field. And now alpha squared is a stochastic parameter that follows an exponential distribution. Okay, so now let's look at the microscope. So microscope, it's a space mission that aimed at detecting UFF violation by measuring the differential acceleration between a platinum test mass and a titanium test mass. And their final constraint on this eta parameter is 10 to the minus 15, which is currently the best constraint on this parameter. And so to do so, they used 19 individual sessions where the noise is Gaussian. And so basically to analyze this data, what we did is that for a given axion frequency omega A, we combine the sessions such that the full time covered by the group of session is smaller than the current time, which means that effectively we are in the monochromatic regime, and we fit a monochromatic signal to this set of data. And again, our signal is modeled as this expression with the stochastic parameter alpha squared. So now let's look at the result. So to analyze this data, we use Bayesian parameter inference again. So the first thing that you need to do is to marginalize over alpha squared because it's a nuisance parameter. A second important part of our data analysis is to use a non-informative prior. So for example, a Jeffers prior. And so the reason is that if you naively wanted to use a uniform prior, the problem is that in our case, it leads to a posterior that does not converge. And of course, this is annoying. And so in this case, we need to be careful and use more advanced priors. And so this is the one we choose. And finally, of course, we computed the Bayes factor, considering on one side a model with no axion-gluon coupling, and on the other side, of course, our model of axion-gluon coupling. And in this case, the model and not without coupling is preferred, so it's compatible with no signal. And so it allowed us to set limits, new limits to this axion-gluon coupling. And so this is what is shown on the right panel. So in gray background, it's the already constrained regions from biolaboratory experiments. And in red is the new constrained region by microscope. And so you see that microscope is able to improve the current limit by several order of magnitude of mass and also of coupling. So this is great. Okay, so I arrived to my conclusion. So what I've shown you is that current oscillations, scalar dark matter induce current oscillation of test bodies. In LISA, this can be seen through Doppler shift of light, which is similar as what do the gravitational wave. Now, in fact, LISA, we show numerically that LISA will be probably able to break the degeneracy between a gravitational wave and a scalar dark matter, due mainly to the polarization differences between the two waves. Now, second thing is that these current oscillations are atom dependent, so they induce UFF violating accelerations, and so they can be probed in by classical test of the universality of field like microscope. And so I've shown you in the second part that you can use microscope data to search for the axion-gluon coupling. And so this is what we did. And we found no positive signal. And this allowed us to set improved bounds on this coupling. Thank you very much.